Get going on sorting 2. So last week we actually on Monday we started doing some sorting, talking about sorting. This week, or today rather, we will start talking about some other sorting. And I wanted to throw up a little comic. A couple people sent it to me actually, and I've seen it lately. Let me see if I can find it real quick. You guys know XKCD? It's a great comic. Online comic, XKCD, and then sorting. Randall Monroe did some sorts here. He called this one ineffective sorts. It's a little hard to read some of this, but it's a lot of reading, but it's actually kind of funny. There's this thing called Quicksort, which we're going to talk about today. Merge sort, we're going to be talking today. We talked briefly about BOGO sort the other day. And then he defines this one called panic sort, which is actually kind of funny. I tell you what, I'll put this up again at the end, and you can read through it. But it's definitely an interesting take on sorting. Okay, we'll put that up at the end. All right. So we're going to talk more about sorts today. And the various sorts that we talk about are more advanced than the ones that we covered the other day, and in fact many times better, although heap sort's pretty good. The lab I heard was a little tricky, a little bit of logic in there that was a little tough, but hopefully most of you guys figured it out in the end. So here's what we're going to do today. We're going to briefly talk about a little Unix tip of the day, a program called sed, which you may never have heard of, but it's an interesting one, and it allows you to change things in a file pretty easily. So it's kind of interesting. And then we're going to talk about a bunch of different sorts, some that we rarely talk about. People don't really talk about this one too much, so we'll talk about some other interesting sorts at the end. But the two big ones we're going to get today are merge sort and quicksort. Okay, both generally recursive sorts, and also both very, very fast. So we will talk about that. All right, any questions before we get going? Anybody started the homework yet? Looking at the sorts? Hopefully that's going all right. Again, I don't think it's too taxing, but hopefully gives you a little bit more of an opportunity to check out, to actually do something kind of independent of like an explicit direction on your stuff. You have to like code some stuff from scratch and so forth. Actually, I forgot. Hopefully, did you guys get the email I sent about homework 5? Yeah, I meant to talk about it, but due a week from today. And if you have other questions, feel free to shoot me an email or come to office hours. Okay? All right. Unix tip of the day. There's this program called, there's a lot of writing up here, called sed, which stands for Stream Editor. Actually, the first editor was just called ed, for editor. And then it's been supplanted, or I guess enhanced, by making it a stream editor, which what they mean by that is if you have a bunch of text and you stream it through this program, the program will be able to take various parts of text and change it for you into something else. Why would you want to do that? Well, there's lots of different times you might want to say do a search and replace inside a text file. And you could do it in an editor, but you can also do it just straight from the command line if you want to. So for instance, if I type sed and then s, which stands for substitution, /green and then /blue, and then g, which stands, I don't exactly remember what it stands for. It's like basically the end of like the input. Then it will change all instances of green to blue if you pipe in a file and then pipe out another file. So from file 1, everywhere it said green, file 2 will now have blue in it. Okay, let me show you that. Okay, so I happen to have you guys know the green eggs and ham, like Dr. Seuss, right? If I type it out, green eggs and ham, it's, I do not like green eggs and ham, I do not like them, Sam, I am, blah, 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 right? Well, green eggs, etc. So if we do this sed command, and change all the instances of green to blue, then it will, and what I'll do is I'll leave off the actual output file. Just know that if I piped it to an output, the output will go there. But if we do that, then everything that was green is now blue. Okay? Blue eggs and ham, et cetera, et cetera. And you think, OK, so it does search and replace. Well, What's interesting about sed is, first of all, you don't have to, if you had slashes, you can actually change the little slash is just any character, and it just, as long as that's not in your search and replace, you can use that. So S:, like to love would change all the instances of like to love. But there are a ton of options to sed, just like most Unix commands. There's like a billion different options you can do. Okay? Here's a little tutorial, and all these things are telling you various different things you can do with sed. And it just goes on and on and on and on and on, right? And this is just like, yeah, it's just lots and lots and lots and lots of, there's the one we just used, right? Lots of things there. And you can use it to do lots of text manipulation. So if you ever do a lot of bash scripting, or in other words, writing little scripts in the terminal, using programs like this is kind of cool, okay? What's really interesting about this is the actual thing inside here, right now it's just a word, like green or whatever, right? But it doesn't have to be. It can be what's called a regular expression, otherwise known as a regex. And regular expressions actually match words, but they match like wildcards and digits and letters and uppercase and lowercase and all sorts of different options. So not only can you like change green to blue, but you could change every instance of G, uppercase R, uppercase E, EN to B, lowercase l, lowercase u, etc. You could like do all the options to make it do a ton of different things. Okay? Regular expressions, there are entire courses like dedicated to regular expressions. When you get into Comp 170, and possibly even in Comp 105, which is programming languages, and then Comp 170 is theory of computation, you will learn more about regular expressions. And in fact, I have, later in the semester, I have another little Unix tip of the day, which is more on regular expressions. But they're really powerful. And actually, they kind of go to the core of a lot of computer science ideas. So while this looks like it's not doing that much, you're like, OK, it's doing search and replace. Under the covers, it's doing a ton of things. And if we wanted to make these searches really detailed, and the replacements really detailed, it can do that for you. So if you want to look up regular expressions, it's pretty cool. Like, it's a huge topic. Okay, so we'll get to more of that later. All right, that's like a little like preamble to regular expressions, which will come later in the course and then in other courses. Big topic in computer science. Questions on sed? I didn't think there would be. OK, let's do a couple more sorts. All right, so we're going to talk about this thing called a merge sort. Merge sort is another sorting algorithm that is comparison based. Okay, in other words, you've got numbers that you're comparing with each other. One is greater than, less than, or equal to the other, and you're doing these comparisons and reordering things based on that comparison. Okay, merge sort is what we call a divide and conquer sort. Aha, we've heard divide and conquer a couple other times. What kind of behavior does divide and conquer normally give us asymptotically? Logarithmic. Okay, so this is the first sort that will give us a nice logarithmic behavior. Now, we got a little bit of logarithmic behavior in shell sort in very certain circumstances. But for the most part, this one is definitely logarithmic. And you'll see exactly why once you see the algorithm. Okay, so basically, the idea is, first of all, it can be coded recursively, which is going to make it a little nicer to learn. I think I might have mentioned this the other day. Maybe I forgot. But when you do merge sort not recursively, it's really hard because of the way it's actually built. So it's hard to do not recursively. And it's also hard to do what's called in place, which we mentioned too. But we'll get to that. Okay? But you're merging sorted lists. Okay? So in other words, if you have two lists, notice this one is already sorted, and this one is already sorted. Okay? And we want to create the sorted bigger list from these two. Okay? Here's what I want you to do. Write down this list and this list, or you don't even have to, but basically figure out how to merge these two lists with maybe a for loop, right? And go through these two lists and merge them together. Do that right now with your partner or your neighbor, and see if you can figure it out. Now I'll start writing some stuff on the board. See if you can figure out how to merge those two lists together. They're both, let's say they're both arrays, two arrays. Oh. Why did you just stop talking? Because I wrote down this weird like length max of L1, L2. Just pretend they're the same if you want, same length. Who thinks they know how to do it at this point? Yeah.
You take the first element of both lists, which is bigger, put the smaller one in.
Okay, hold on. So basically you're basically gonna put the. So I guess we're not gonna write it out like this then. I guess we won't do like a for loop. But in your case, what do you want to do? You want to take the L1 and L2, and what do you want to do?
You compare the first element of L1.
Okay, so before we even do that, let's say that we have an index of like the first of L1 and an index to L2 in the first one, right? Because that's the first thing you have to do, right? So let's just put little arrows here for there and there, and we'll call this I don't know, lowercase L1, and we'll call this lowercase L2 like that. Okay, so you're going to do what? You're going to compare if L1. Okay, so then put small L1 where? Okay, we'll call this I. Okay. So then we're gonna have. I guess we could have written it out in code. We're going to compare lowercase L1 and L2 to what's in the arrays there to each other. The smaller one goes here, and then you do what? You increment L2 and then I. Okay. And so now L2 is going to be here. Oops. L2 is there, and I is here now. Oops. I'm mixing up my I's and T's. All right, there we go. And I is there, and then what? You keep, well, OK, but then maybe you keep going with L1 and 2, but what if you run out of one of them? OK, so then you put the rest of the other one in. OK, so that makes sense. So did everybody get that? Basically, you walk through this list. You compare the first two elements. The smaller one goes in your list, if we're doing from smallest to greatest. Smaller one goes in your list. Then you increment the place in the new array. And you increment the place in the one that had the smallest one. And then you repeat the process where you look at L1, the array, the value in L1 versus the value now in L2 at the new position, and put the smallest one there. But if one runs out, you just put the rest of the other. OK, so in this case, it's going to be, now we're going to compare 8 and 3. OK, and the 3 is smaller, so 3 is going to go here. I is going to go here. And L1 is now going to get incremented there. OK, and then we're going to do the same thing. And now we're going to put the 5 in here and increment this one like that. Let's see. Now we've got that's L1. And now the 5 is there. And I now points over here. OK, and then we do the same thing. And then the 8 goes in here. And this one gets not the best example in the world because we didn't actually run out. Well, we'll run out in a second. But 8, and then this one goes here, and I is now here. And then the same thing happens again with L1 and L2 over there. So now the 10. And then we run out. So I guess we do run out here. And if we've now gone past the size of one of them, then the rest of the other one goes in. OK? That is called a merge. OK, and that's how you actually do this. All right, same thing here. There we go. Bing, 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 bing. And we finally do that. OK? Merging two lists is easy, right? It's a simple for loop. We didn't actually draw it, but it's a simple for loop. And you have to do a couple checks here and there. But that's a nice, easy way of going through that. OK? The full merge works like this. OK? Divide the entire list into n sublists. So if you have n numbers, you're going to have n sublists, right? And each sublist is now a single element. OK? And then you repeatedly merge the sublists together. So you have two elements that are single elements. Is a single element already sorted with itself? Like it's already sorted, right? no matter what, a single element is sorted. If you have two elements that are sorted, then you merge them together, and they may stay the same or they may swap, but those go into a new array. And do the same thing with the next two, and the same thing with the next two, and the same thing with the next two. And now you've got half as many total groups, because you've merged all of them into half as many groups, because you've taken two into groups of one into groups of two. And then you do that again, and then you get a half again, and then a half again, and then a half again, and eventually your entire set of numbers has been completely merged into one sublist, which is your sorted list. OK, that's kind of nice. OK, watch how it works. 99, 6, 86, 15, 58, 35, 86, 4, 0. Not a sorted list. We're going to break it into individual pieces, but we're going to do this part recursively. OK, we're actually going to do the whole merge sort recursively. So the first thing we do is break this into halves. OK, like this. OK, break it into halves. And if your one half is slightly big, is one bigger, doesn't really matter. Won't matter in the end. OK, we're recursively going to do this, and you'll see the recursive algorithm later, or the actual code. And we're going to recursively do it into two lists. And then this one gets recursively broken down into two. And this one gets recursively broken down into two. And then everybody gets broken down into two more. And then finally, these ones, which is still a group of two, gets broken down into two more. OK? Notice we've gone through, and now it's half, 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 half. And then we're down to single elements now. OK? Then you start merging back together. OK? Because these two are individual, like one element lists, now you can merge the 4 and the 0 together. And doing that, using our little algorithm from before, this one will become 0, 4. Right? So that actually becomes 0, 4. And it ends up being merged together like that. These two now get merged together. They actually are fine. OK? Oops, sorry. These two get merged here. Sorry, this one and this one get merged. Then these two piles get merged. Right? These two get merged, then these two. It's a little weird because of the fact that there's an odd number. But basically, we first merge these, then this one, and these two groups get merged. Then these two groups get merged. These two groups get merged. These two groups get merged. And then you've got here, and now you've got 2, 3, 4 groups. Now this one and this one are going to get merged. And this one and this one are going to get merged. Like that. OK, lots of arrows everywhere. Everybody gets merged back into there. And now we've got an almost sorted list, actually. This one is now sorted, and this one is sorted. So now we're going to merge these two together. And we are back up to our original, where we have a completely merged list. OK? You broke it down by halves. And in so doing, we've got logarithmic behavior. OK? Notice the number of steps here is basically the log. It's very tree-like in some sense. Right? You're breaking it down into smaller and smaller pieces. OK? That's merge sort. OK? You could do it in place, but it takes a lot of time to do it in place because you have to shift a lot of elements. Imagine doing that in place where you have like, well, this is the sorted list, but you're trying to merge, breaking them all down, and then all of a sudden you're trying to merge these guys. OK, they'll have to swap with each other, so you got to have a temporary somewhere. But then what happens when you're merging like this section with this section? Well, both of these might need to go over here, and both of these might need to go over here. And so it gets a little bit tricky. So doing this in place, while not a terrible idea for your homework assignment, would be very hard. OK, I've seen people try it before, and it gets confusing. OK? All right. Merge sort is not in place generally at all, so we end up using basically twice as much storage. Okay, because you're going to have to create enough smaller arrays that are basically the same length as your original one to actually do this. So it's not an in-place algorithm, and it definitely takes up a lot more space than you would necessarily like. Okay? However, it's very fast, because you don't need to shift any elements. It takes double the memory, but it's not particularly memory efficient. Okay? It does happen to be stable, though, which is kind of nice. Yes?
Isn't there going to be more than double the memory because you also have all the
depends how you build it. Depends how you build it, but yeah, sometimes you can actually get away with just one more total array if you want. Like the way it works out, because everybody gets broken into halves, you only need to go up. You only need to go back up. Think about it this way, right? This array is really the same as this array in the end. Like you can end up doing it so you only need twice the storage, as it turns out. Okay. Yeah. All right. So worst case, n log n. That's good. And the n comes from the fact that you have to go through lists for each time anyway. The log n is the part where we're breaking it down logarithmically. And remember, that's the best we're going to do for for comparison sorting. Can't do any better than that. Best case, also log n. Average case, n log n. And average case is n log n. So this is another one of the very good sorts. Much like heap sort, it's very good in terms of being fast. And it's pretty easy to code. All things considered, it's not that hard. If you choose a merge sort, you'll find out that, oh, it's not that bad to code for your homework assignment. Okay? Merge sort, a good one. But again, if you're memory conscious, then not the best one to do. Okay? All right. Now we're on to Quicksort. As I mentioned the other day, I think Quicksort is one of the it's one of the first real algorithms you see. Now the other ones are algorithms, but this one's actually, somebody had to really think about this one, right? To come up with this, they had to go, oh, I kind of get what's going on here. Okay, I mean they had to say, hey, this is a different way of looking at sorting, and it's interesting in the sense that, and I'll show you the example on I'll show you the example online that shows how it works. It is most often the fastest sort you'll get for randomized data, okay? Which is why it's called Quicksort, and it's also why we use it a lot, okay? However, on average it does have, and most often it has n log n behavior. It can have a worst case behavior of n squared, okay? Which we don't like. And it turns out that the n squared behavior can come up in times very often, and you'll see why when we get there, okay? So this is one of those ones that it takes a little bit of wrapping your head around, but we'll walk through it slow enough, and we'll go over it a couple times that I think you'll get it. But it's also the kind of one that, so I did a little poll of some of the graduate students and some of the upper level undergrads, and I said, how many times have you been asked about Quicksort in an interview? And everybody said at least once. So in an interview, you have a very good chance of somebody saying, what's Quicksort? What would it look like? What does it do? What's its behavior? Okay, so definitely make sure you know this one. Even if you don't know any of the other ones, make sure you know this one. Okay? All right. It is definitely another divide and conquer. Okay, that's really the only way we're going to get this great logarithmic behavior that we like, the n log n behavior. But here's the basic idea. Divide a list into two sublists. There's your divide and conquer, where the lower elements and the higher elements are in those lists. Like one list contains the lower elements, and one list contains the higher elements, for whatever higher and lower that means. Okay? And then what you do is then you basically recursively sort, and then you recursively sort the sublists. And if you keep doing that, where you get smaller and smaller lists, where some of the smaller elements go in one list and the bigger elements go in the other list, eventually you will have a whole bunch of small lists where everybody's now in order. Okay, it seems similar to merge sort, but we're not merging so much as we're partitioning into different piles. Okay, I'll show you what we mean by that. Okay, here's how it goes. And this is the algorithm part that people will probably ask you about. Okay? In fact, I'll ask you about it on the final in some form or another. Pick an element, one of the elements in the array. Which one? Well, we'll talk about that in a few minutes. Okay? Reorder the array such that all the elements with values less than whatever that pivot was come before the pivot. In other words, you're taking the array and you're doing this in place. You don't have to do it in place, but you can do it in place. And if you pick a pivot and then change it so that all the elements that are smaller than the pivot go on the left side of the pivot, and all the elements that are bigger than the pivot go on the right side of the pivot. Okay, then you've got what? You've got a pivot with some smaller elements and some larger elements. Okay? That's called the partitioning, right? And the pivot is now actually where it's going to be, as it turns out. Because why wouldn't it be? Everything else is smaller and everything else is greater. It's going to be exactly where it needs to be. Okay? Then you recursively do the same thing to each sublist with smaller values and separately to the sublist of elements with greater values. In other words, you do the same exact partitioning of the smaller sublist and the larger sublist. Okay? You can actually ignore the one that you just partitioned if you want. It actually makes it slightly faster. If you don't, it really doesn't matter. Okay? And then in the recursion, the base case is when you have a list of 0 elements or 1 element. Because as we all already said, a list of 1 element is already sorted. Also, a list of 0 elements is also already sorted. Okay? So that's your algorithm. Okay? And as I say, this is an algorithm where somebody said to say, hey, this is a different way of thinking of this. This is like a real computer science algorithm where somebody said, let's change things up the way we think about this and make it work. Okay? It's not particularly hard to understand once you get it, but it was probably hard to understand, hard to figure out in the first place. Okay? So there is a naive algorithm which is not in place. Just create a new list for each subsort. Okay? That's kind of like the merge sort way where you're just saying, here's a new list, go, right, with your new list. And the overhead is now an additional memory, right? Same idea as before. And you can reuse the previous list if you wanted to. But we can also do it in place. And it's the in place one that I want you guys to know how to do. Okay? So let me show you how the in place one works. Okay, let's do the naive case first. Okay? Let's say that we have our array here, and we pick our pivot as the first element. Okay? 6. So now we're gonna create a new array where all the elements less than 6 are to the left of it, and all the elements bigger than 6 are to the right of it. Okay? Like that. Okay? You can pretend this is one array or two arrays, doesn't really matter. Okay? So now you've got that, and then you've got 6 kind of in the middle here. Okay? And then you do it again. Now you say this one, let's pick the pivot as 5. Okay? And so now you've got all the elements less than 5 are on one side, and all the elements greater than 5 are on the other. But guess what? 5 happens to be the greatest element, so there isn't a greater than 5. There aren't any in that one. Okay? And then the same thing here. Pick the 9 and the 12. Well, this is a subset of 2, so really it's just going to be nobody's going to be less than 9, and only 12 is going to be greater than it. Okay? And we have to do it once more for the 3 and the 4. Okay, we're going to take the pivot as the first one again. In this case, we're just always picking the pivot as the first value. Why not? Okay, pivot's the first value. And then everything less than 4 goes over here. Everything greater than 4 goes over here, but there isn't any. So that's that. And then, as it turns out, there we go. Now, look what we've just done. 3, 4, 5, 6, 9, 12. Okay? Reordered correctly by just doing this. Pick a pivot left and right. Yeah, Zoe. Sorry, why are the pivots sorted in the middle? They get sorted kind of by default. Right? I mean, you basically say, OK, our pivot is 6. That's going to go in the middle. Like you say, that's going to go in the middle. And then you're going to have 2 lists, one on the left, one on the right. Right? And the left one's going to be lower, and then you've got basically 3 lists. But you forget about the one in the middle because it's already sorted. It's already in its correct place. Yeah?
So does the speed of the whole thing basically depend on how you're finding your pivot? Like how you're choosing that?
Does the speed depend on how you're choosing your pivot? How you choose the pivot may determine whether it's fast or not.
Yeah, it's like you pick like the smallest one every time and take one.
Yeah, if you pick the smallest one, that's actually the problem with this, right? If you pick this, let's say you pick the smallest value every time, right? And then you're always going to end up breaking it into like a 1 element and then the rest of it, right? So that's actually one of the problems with this. We'll get into a little bit more of that later. Good call on that, okay? But before we worry too much about that, let's look at the in-place algorithm. Now, this is the one that's going to take a couple minutes to sink in, I think. Okay? Here's how this works. You've got this Quicksort function where you pass in the array, and you're going to pass in the first element and the last element, like the index to the first element and the last element. Okay? We're going to pass in array and the first element and the last element. Okay? And for now, we're just going to pick the first element as our pivot. It's just going to make things a little easier. Okay? Later, we can figure out how to not do that. But for now, we're just going to pick the pivot there. OK, now watch what we do. We are going to start two other indexes. They're not pointers, although they have arrows on them. They're just indexes to the location of the left and the right. Okay? Right is going to move to the left. Okay? And left is going to move to the right. But they stay left and right of each other, basically. Okay? Does that make sense? Left is going to start going this way, and the right one's going to start going this way. Okay? Right goes to the left until the value should be to the left of the pivot. So in other words, we're going to look at the right one, and we're going to say, should 4 be to the left of the pivot? It actually should, right? So we're going to stop moving this one. Okay? You have to do it in this order. You could do it in the other order, but you've got to make some other assumptions. Just do it in this order. You'll see that it works. Okay, so we're going to say, OK, right is going to move to the left until the value should be left of the pivot. Well, it already is. So now we're going to say left is going to move to the right until the value should be to the right of the pivot. Should 6 be to the right of 6? No, it can't be, right? So this left is going to go here. Should 5 be to the right of 6? No, because it's less than 6. Should 9 be to the right of 6? Yes. Guess what? Now you have two variables. One should be to the left but is somewhere else. The other one should be to the right. What do you think you're going to do with those two? Swap them. Okay? So here we go. We're going to do that. And then now we're going to get to 9 and 4. 4 should be to the left. 9 should be to the right. Swap them. Okay? And you keep doing this until the left and the right cross each other. But remember, you've got to do it in the correct order. You can't go, OK, now the left is going to go this way. No, no. You've got to go back and do the right one. Should 9 be to the left of 6? No. So you move it here. OK? And you don't like try to fool yourself and say, don't try to like be sneaky about it and go, oh, just move it here. Don't just watch. The algorithm will work on its own. You may have to do one or two more. There are ways to make it a little bit more efficient, but you've got to be very particular about how you do it. So just follow this one right now. Should 9 be to the left of 6? No. Should 4 be to the right of 6? No. 12. Should 12 be to the right of 6? OK, so oh, sorry, I did it wrong. Right? Should 9 be to the left of 6? No. Then you move to 3. Should 3 be to the left of 6? Yes. Then you're going to move left. Should 4? No. Should 12 be to the right of 6? Yes. You're going to then swap those. We'll go through that here. OK, that one's going to go there. That one's going to go there. OK, they cross. I mean, sorry, they are in the proper place where they should swap. OK, we're going to swap those. OK. Should 12 be to the left of 6? No. Move it here. Guess what? They just crossed. They basically are now going to be the same. OK, like that. OK. Now, as it turns out, if you've done this correctly, this value that you're on should be a value that you can actually swap it with because remember, the last thing that it was a value that should be smaller than 6, because you just swapped it there. Right? So this value now should swap with the pivot. And guess what we've done? Here's our pivot. And everything to the right of the pivot is bigger. And everything to the left of the pivot is smaller. Okay? Let me go through that again. All right, if you got it, be smug. If you didn't get it, you'll see it again to see how it works. OK. Pick the pivot. The pivot is 6. Okay? So we're going to remember to compare against 6. Okay? We have a left and a right. And the first thing we're going to do is the right is going to start going left until it should be to the left of the pivot. And then we're going to do the left one going right until it should be to the right of the pivot. So 4 should be to the left, so we stop moving the right. We didn't actually move it. The left, 6 doesn't matter. If you wanted to be sneaky, you could move this one up here, but you just have to be a little careful because there's all sorts of corner cases if you don't follow the algorithm exactly. Okay? So 6 should not be to the right of 6. 5 should not be to the right of 6. 9 should be to the right of 6. Okay? When you get in that case, you've now found a value that should be to the left and a value that should be to the left and a value that should be to the right. You swap them. Okay? And then you repeat the process. Well, the process started with, should the one on the right be to the left? No, 9 should not be to the left. Go to 3. Should 3 be to the left? Yes, it should. Now go to the left one. The left one, should it be to the right? No, it should not. So we move it to there. Should 12 be to the right? Yes, it should. So now we're going to swap them. Okay, 12 and 3 get swapped. Now notice again, 12 and 3 got swapped, so this 3 should be to the left of 6, which is the pivot, which is fine. Okay, repeat the process. Should 12 be to the left? No. So move it to the left. They have now crossed each other. They're, in other words, left equals right. And when that happens, swap the pivot with the one you're at, and you've done it. Okay? So you've seen that a couple times now. Go back and look at this 100 times if you want. That's how the algorithm should be written. Okay? A lot of people pick Quicksort for their sorting assignment, and then they try to be sneaky about it. And they say, well, I don't need to start it at 6. I can start it here. And I don't want to, I want to pick the one in the middle and pivot over that one. Just be careful if you do that. There are going to be corner cases. Yeah?
Does the pivot have to be at the far left?
For this algorithm, it does. Like, the pivot has to be at the far left. Now, the question was, what if we pick, see, let's go through what happens here. In fact, it might be on the next slide. I forget. No, it's not going to be. We'll talk about this right now. If we always pick the smallest one, we end up in trouble, right? Not really in trouble, but we end up doing what? If we always picked the smallest one, then it would always end up on the left, and everybody else would end up here. And then the next one partitioning you do is on everybody but 1. That's not a good thing, because you want to break this into more or less half, right? So if you do that, what ordering would this be really bad at? Any ideas? If we started out with an array in some order to make Quicksort break using this algorithm, what order would that be? If it was already sorted, right? And lots of times you might apply a sorting algorithm on numbers that are either almost already sorted or actually already sorted because you're not sure if they're sorted yet or whatever. And so, oh no, that would be bad. So Quicksort actually breaks down in a bad way if things are already sorted, which we will get to how to fix that in a little bit. Yeah? Kate. That's the way the algorithm works. Okay, so you basically just say check the right, start the right at the far one, start the left at the far left, and then start with the right checking and doing it that way. So this is why I said it's kind of the first algorithm. This is like the first one where you're like, oh, there's a big algorithm here to actually walk through, right? And it's not really intuitive when you first see it. Okay, but that's how it works. Yeah? Sure. Let's say, let's do this one. OK, so I'm about to swap the 4 and the 9. OK, I just start the whole algorithm over again. I say the right, check the right. Is it supposed to be less? Should it be to the left of the pivot? Well, by default, it's not going to be because you just swapped something into that one. OK, but don't try to be too tricky about it. OK, this is one place where you probably could be tricky and say skip that one. It's going to be here, but just be careful. OK. The way it's done on the slides will work. If you try to be fancy about it, you might break it, and you'll have to figure out why. OK, that's that. OK. All right. What you do now is you just return the index of the pivot, and that tells you where you're going to recursively call the next two. So basically, we're going to return the index of the pivot. So in this case, index 3, right? And then we're going to recursively call Quicksort on the 2 new partitions. Right? 0 to 3, or you could get away with 0 to 2. In fact, it would probably work just as fine if you did 0 to 2, because 6 is already in the right place. In the end, 6 will definitely be at position 3. But it's not actually going to matter. It's a couple more instructions, but it's not that big of a deal. But this case, you've just got 2 lists. Otherwise, you'd have kind of 3. But if you do this now you quicksort this guy and quicksort this guy, doing that partitioning thing with the exact same algorithm. In other words, check the right, check the left, etc. OK? And we're going to do that. So the right moves to the left until it should be to the left of the pivot. This is our pivot. Should 6 be to the left of 3? No. So it should go there. Should 4 be to the left of 3? No. So it should go there. Should 5 be to the left of 3? No. So it should go here. Should 3 be to the left of 3? No, but guess what? They actually cross. Actually, before you even do that, 5 to the right goes this way. They have now crossed. You don't even need to check 3. What do? Swap with the pivot. What swaps here? Nothing swaps. You can go through the motion and swap. It's fine, but nothing will actually swap. So this is a situation where we were just talking about. This is the situation where the pivot happened to be a bad choice, right? You now do have 2 elements to sort, but this was a bad choice. You only got the benefit of, you didn't even really do anything, right? You got the benefit of like 1 extra value, and that's it. Okay, and then let's see, let's cross there, and then you would have quicksorted this one as well. Let's see. I think we're going to do quicksort on this one, and then quicksort on this one. But this is the base case. There's only 1 element, right? And so you don't need to worry about sorting that. This one, you're going to sort this one. You would pick 5 as the pivot. That's actually a good pivot, right? And you would end up quicksorting this one. When you quicksort this one, you get 9, 12. When you quicksort this one, you get 4, 5, 6. And you get 3, 4, 5, 6, 9, 12, which is your sorted array. Okay? So it actually ends up happening. It's all in place, and there's no like needing to copy values around. Okay? Yeah?
You have to call quicksort on the array 0, 3, because you're already know 6 is going to be in index 3. You just call quicksort array value.
Yeah, well, right. The way I did it on here, it just makes fewer boxes. But yeah, you could in this one you could call quicksort 0 or quicksort 1, 2 to get to this one to begin with. But you just have to be a little careful because sometimes you could end up calling, if you do it wrong, you call like quicksort 0, -1, and then you're in trouble, right? So you just have to be a little careful on. Again, it will work this way with some more, like a few more lines of, or not lines of code. If you'll have to do things a few more times, still logarithmic, not quite as fast. You can be tricky about it, but get it working first. Then say, how am I going to tweak it so that I don't worry about doing the 6 again? All right, that's kind of my suggestion in that case. Other questions on this? On how quicksort actually works? OK. So here's what we already mentioned this a little bit. The decision about choosing the pivot is actually super duper important. Okay? If the leftmost one is chosen and our array is already sorted, we actually end up with n² behavior, which is terrible. Why does it end up n² behavior? Because every time you do quicksort, you're doing, let's say you have 10 elements. Your first one is going to do 10 elements, and you're going to end up with a 1 and a 9. Then you're going to do 9 elements. You're going to end up with a 1 and an 8. Then you're going to do 8, and you're going to end up with a 1 and a 7. And you see how it's n² behavior for every time you're going to have to go through the quicksort thing n times for every element. So it's not a very good solution or situation. So what do you want to do? Choosing a pivot that's random works pretty well. In fact, it works really well. Most quicksorting implementations choose it that's random. And you can actually choose what's called a pseudo-random number, because it doesn't actually have to. So we won't go into the details here, but you know, like if you roll a die or dice, you get random numbers out of those, supposedly, right? Like that's kind of you hope that your die is not loaded in some way to like make it so they always come up with a 2, unless you're a gambler or whatever. But when you roll your dice, that's a real random number. Okay? A real random number is impossible to get mathematically. Let that sink in for a second. There is no mathematical way to get a real random number. Okay? Because you can always recreate that pattern and then it would be the same numbers again. So it's not random. It's what we call pseudo-random if you're doing something mathematically. You can use mathematical functions to make pseudo-random numbers that they look random, but they're not really random. Okay? Yeah, Ben?
I just have a question about choosing pivots that are the leftmost element. If you're choosing the leftmost element, you never have to worry about your left or your right hitting your pivot.
Yeah, very good point. That's a very good point. I was going to tell you that in a second, but I'll talk about it right now. If you pick the leftmost one, the algorithm works great because you never have to worry about skipping over that pivot or somehow dealing with the pivot. So the best thing to do is whatever you pick for your pivot, do one swap and make it the first one. Right? So let's say you have some fancy way of picking the pivot. Just swap it with the first one and now go with your algorithm, and then it will work perfectly fine. But yeah, that is a very good question. There are sneaky ways of leaving the pivot where it is and skipping over it and then remembering to go back, and it's just a little trickier. Then you have to figure out should that element be to the left or right or the other one at the end? And that's what you have to figure out. But yeah, good point. Yeah.
Is it worth it to check if the list is already sorted?
Ah, that's a good question. Is it worth it to check if the list is already sorted? So you get n squared behavior for already sorted. Let's say the elements are 1 billion elements. OK, so you're going to say, OK, you know what? It's going to be worth it if I check and see if it's sorted. Where's your cutoff point for sorted or not?
As soon as one is.
OK, so then you've taken the time to go through, and then two elements are out of place. Can't be just one. Think about that for a sec, right? Kind of impossible. It's like a monopole or something. It's impossible. But 2 elements are out of place. Out of 1 billion elements, have you changed the asymptotic complexity at all? It's still going to be n squared, isn't it? Yeah. So really, there's no real way to do that check efficiently. You might you might be able to come up with some sort of heuristic that says, OK, if certain percentage are in order, whatever that means, and it's hard to, how do you know if something's in order heuristic? I mean, it would be really hard to do, right? And again, every time you do something that tries to go through a list, you're adding on another linear behavior just to do that, right? So in the end, in some cases, you might get away with like doing one linear thing and then not worrying about it, but it's still a linear behavior. So I think you'd be in trouble trying to do that. But good question, and that does come up occasionally, and you'd think it might be, but even if it's off by just one swap, then you're still going to be n squared in the end. Yeah?
What if you were to choose the average value?
Yeah, what do you mean average value?
So while you're going through the array and moving through your stuff, for each element, add that on to like a variable that you're storing, like an integer variable that you're storing.
Uh-huh.
And then at the end, calculate what the mean is for that list and have that be the pivot value.
OK, it would have to be like the median, not the mean, though, because then all of a sudden you never have the actual pivot. Now, sometimes you might not get the pivot, right? Like if you have two numbers that the average is a decimal instead of an integer, right? You'd be even careful. But there might be some ways of doing that. Yeah, it would probably be a little more work than you really need to, right? But I like the idea of finding something in the middle. It turns out if you actually choose the value in the middle, that's actually pretty good, right? You can come up with a way that if like it's sorted kind of opposite way, like sides or something, then you'll end up it would be hard to come up with something that would be really bad for if you choose the middle element versus the left element. Many times things are in sorted order. Not many times they're in some weird, like this one's in order, then these two, then those two in the middle, then those, it's going to be a little weird. So picking the one in the middle is actually pretty good. All right. So if you can come up with a quick pseudo-random way of choosing it, which is actually relatively easy to do, that's good. Or choose the middle item, right, which is the middle of the list, then you can do that. Careful choosing the middle. This is actually an interesting little point here. If you choose the middle item, if you choose left plus right divided by 2, that can actually what we call overflow, which you might not have heard about before. But you know how we deal with basically 2 different types of numbers these days, 32-bit numbers or 64-bit numbers. Okay? If you have a regular old int a, if you say int a, you are generally given a 32-bit number, which means there are 2 to the 32 numbers that are representable. Okay? Anyone happen to know what 2 to the 32 is approximately? You will once you become computer scientists. 4 billion. Okay? So 2 to the 32 is about 4 billion. If you have half of those negatives and half of them positive, you only get 2 billion positive numbers. Let's say we're sorting positive numbers. If you only get 2 billion positive numbers, what if your array was 1.5 billion long? Okay? That's a big number, right? But you can just, it might be that big. If it was 1.5 billion long, if you tried to, and the left and the right happen to be like in that range of the upper half of that, couldn't you end up with 2 numbers that are bigger than 2 billion? Like 1.5 billion and 1.6 billion. If you add those 2 together, you end up with a number that's bigger than 2 billion. That causes the computer to say, I can't represent a number that big, and I'm going to overflow. Now, all of that is to say that if you try to do this, left plus right divided by 2, most of the time you will be perfectly fine. But if left plus right Remember how a computer does things. It will add left and right and store it somewhere temporarily. Maybe this is not remember. This is how it works, right? Left plus right, if you do this left plus right divided by 2, the computer will say, OK, left plus right is some number. Let me store that number. If the number was bigger than 2 billion, it will say, I can't do that. Or it will actually give you garbage is what it ends up doing. It doesn't even stop. It just gives you garbage. Because it's what we call overflows. And that won't work. And then you divide by 2. But if you do it this way, the left plus the right minus the left divided by 2, this is the same exact you end up with the same result, right? If you think about it, this is left plus right. It's left plus right plus left divided by 2, right? And if you do, then it's left plus right divided by 2 plus left divided. Sorry, I subtracted it here. This should be right minus left divided by 2. What's left plus right minus 2 minus left divided by 2? Left divided by 2 plus right divided by 2, which is the same as left plus right divided by 2. So those two things are the same. In other words, these two things are the same, but this one will not overflow. Because if you have a right, which is bigger than a left, you cannot get these two numbers to overflow. It's impossible. OK, all of that is to say, if you're going to choose the pivot in the middle, use this instead of this. OK? Yeah, Kate.
Why can't you just use the array size divided by 2?
Remember, first you've got the array this big. So the first time you could do that. But the second time you've got this array.
But don't you know the size of it?
You do, but so what are you going to say? You're going to say the size of that. Well, how do you find the size? You find the size by basically doing the right minus left is how you would find the size. That's how you would find the size.
The array size divided by 2?
No, because now you've got the same array but 2 indexes. So it's not that you don't have the array size. It's kind of subtle. But when you break the array into 2 pieces, let me just do it. Here's the array. 0, 1, 2, 3, 4, 5. Now we quicksort this. So then we end up with 2 arrays, right? If it was, this is a bad example, but let's say we ended up with 2 arrays. It's really the same array. We're just saying we're going to go here and here and here and here and sort this one and sort this one. And how do you determine how long this one is? You do this value minus this value, right? Which is really the same as this, right? I mean, you end up doing it this way, but just don't. But you know left and right, but you have to figure out which one the one in the middle is. Think about it a little bit. You'll see that it doesn't work out if you try to do it the way you want. OK, that's quicksort. Now, the other one is that quicksort repeated elements actually cause quicksort to slow down. Remember when we showed the, where is it here? Quicksort, no, sorry, sorting visualization. Sorting visualizations. Is it here, I think? Yeah. Here's quicksort on the, actually, I'll just click on quicksort here. Here's quicksort, OK? For a random list, oops, what have I done? Hold on. For the random one, OK, it goes pretty quickly, right? And you can kind of see what's going on. It's partitioning based on the value there, OK? All right, that one's pretty good. Nearly sorted, though, is not going to be so great. Actually, let me just do it this way. You'll just see all of them at once. There we go. OK. OK. Actually, they pick a good pivot. They know how to pick a good pivot. But the few unique, if you have a few unique ones, you're always going to end up with this extra set of, you might not get a good breakdown. Because let's say you pick the pivot of 6, and there's lots of 6s in there. Well, where do you put the 6s? You have to make a call to the left or the right, but it's always going to be one side or the other. The few unique cases really slow for quicksort, no matter what your pivot is. OK, that's a problem. Well, what you can do is you can actually have 3 different groups. Instead of 2 groups, have a middle group, a pivot group, or whatever. And say that anything that's in the pivot group goes in a middle array, and then ignore that middle array. Okay, that's called quick 3. And remember how, let's see, there it is. Remember how they had a quick 3 column here? Quick 3 actually works great with sorted data, or with data that actually has only a few unique ones. Okay, let's see if we can. There it is. Okay, watch this. So it'll actually do it really quickly because it jumps over the whole worrying about that. So boom, it gets done really quickly. Okay, you just have 3 partition groups instead of 2. Okay, so for one of your homework assignments, you might want to try quick 3. It's actually pretty good. Yeah. You do. You need to pass. Well, you don't necessarily need to pass in more indices, but you will have a middle group that you're going to ignore every time. So it actually becomes the middle group gets ignored every time. So it's actually pretty fast in that case. Yeah. So quick 3 is a pretty good one. Most implementations will use a variation of quick 3. Okay. All right. So separate the values into 3 groups instead of 2. Okay. And this will be better performance. Okay. Any questions on Quicksort? Asymptotic complexity, and worst case, n squared. But that doesn't happen often. If you pick a good pivot, you will very, very rarely get n squared behavior. That's why it's a pretty good sort. Rarely will you get n squared behavior. Average time is n log n. Space complexity for the naive is where you have to add this extra amount of space. In place, though, you do have kind of an extra logarithm because you do this recursion, and they kind of count the recursion as taking up extra space. It takes up space on the stack. It doesn't really matter that much, but that's what they define it as. But do not worry about this, right? Space complexity, don't worry about this. This is the one you want to worry about. Best case for Quicksort, n log n. Worst case, n squared, but very rare. Okay? Average, n log n. Okay? All right, questions on Quicksort? All right. The last sort I want to cover, well, we might have time to cover another one, which is kind of neat too. There is another sort called a Radix Sort. Not many people end up learning about this, but this is kind of a fun one. And you might get a question about this on an interview, maybe. Who knows? But Radix Sort is not a comparison sort. It works in a totally different way than comparison sorts. Okay, which is cool. You think, hey, how do you sort things without comparing them? I will show you. Radix Sort uses these buckets, and we'll see buckets a little bit later. Radix Sort uses buckets to sort elements based on which decimal place it is currently working on. So that's a little weird. Okay, you think, wait a minute, what's the decimal place has to do with it? Well, we'll see. Every time you go through, so what you do is you go through the elements a number of times. Okay? And each time you look at a particular decimal place, and that's what you sort on. Whatever that decimal place is, you throw that number in that fits in that decimal place. Oh, I'll show you. That fits whichever one of the 10 decimal places it is, it goes into a bucket between 1 and 10. Okay, Alex is like, what are you talking about? I'll get there. We'll get there in a sec. The buckets are now individual arrays for the digits 0 through 9. Okay, if you have a number, each digit is a 0 through 9, right? That's the definition of a decimal number, right? You've got digits 0 through 9. Okay? Here's how it actually works. Okay? Let's say these are your numbers. Okay? 310, 213. I'm writing it like 0, 2, 3 for a reason, because we're going to have to do each decimal location, and 23 actually has a hundredths digit. It happens to be 0, though. Fair enough? OK. So 0, 2, 3, 130, etc. These are not sorted. What we're going to do is go through this list looking at the least significant digit. Called a bit here, really the least significant digit. In other words, which of the number 123, which digit is the least important? The 3 is, because the other ones mean more. Right? You've got 100 plus 20 plus 3. The 3 is kind of a throwaway. That actually leads me to one of my favorite jokes, actually. Did I tell you that? I forget if I told you this. I don't think I told you this joke. 2 guys walk into a natural history museum. Did I tell you this one? OK, 2 guys walk into a natural history museum. And they see a dinosaur skeleton. And the one guy turns to his friend and says, see that dinosaur skeleton over there? That dinosaur skeleton is 1,000,004 years old. And the other guy goes, how do you know it's 1,004 years old? And the first guy goes, well, I came here 4 years ago and they told me it was 1,000,000 years old. Right? And that's because the significant digits, like the 4 years is not significant, right? That dinosaur will be 1,000,000 years old for another 500,000 years, right? So it's all about significant digits. The least significant digit is the last one in this case. Okay? So we have 10 buckets. Okay? And in fact, in this case, notice all these numbers have only 0s, 1s, 2s, and 3s. It's so I couldn't fit it on the page. But in this case, we only have 3. But I guess these are base 3 digits or whatever, but or base 4. But in this case, 0, 1, 2, or 3. And what we're going to do is if the least significant digit is 0, it goes in bucket 0. If the least significant digit is a 3, it goes into bucket 3. See how we're not comparing the numbers at all? We're just saying go into your bucket based on whichever digit we're working on. Okay? So notice, bucket 0, everybody ends in 0. Bucket 1, everybody ends in 1. Bucket 2, everybody ends in 2. Bucket 3, everybody ends in 3. Does that make sense now? That's our first pass. What we then do is we pull these out in a first in, first out basis. So think queues. You actually use queues to do this effectively. A first in, first out basis, and then put them back into the original array. Okay? Right? That's how they go in there. And then you put them back into the original array. So now you've got the 0s with the least significant digit all lined up here, and then the 1s are lined up here, the 2s are lined up here, and the 3s are lined up there. So far, so good? Repeat the process for the tens digit. Now, if it's a 1, it's going to go in the 1 bucket. If the tens digit is a 3, it's going to go in the 3 bucket. See how that works? 301, 201, 002, 102, guess what? They're all, the middle digit is 0. And by the way, I picked these numbers so they fit in here well, too. It could be that they all have a 0 in the second digit. So bucket 0 would be the whole array, and bucket 1 would be nothing, and so forth. But I picked it such that it fits in this little picture. Okay? But now you've got this. So 310, 111, 213, 013, all digit of 3. Pull them back out into the array, first in, first out way again. And now they're in order this way, 301, 201. Okay, all the 0s are now over here, and all the 1s are over here, and all the 2s, etc. Okay? And then do the hundreds digit, the 3s. Well, guess what? If you now put the hundreds, so the 301 goes here, and then the 201 goes here, and the 002 goes here, etc. Whoops. You now have a sorted array. 2, 13, 23, 32, 102, 111, 120, 132, etc. Okay? Did you ever compare two numbers together? You didn't actually. Yeah?
When you're saying you're using queues, is that each bucket is a queue?
Each bucket is a queue. Yeah.
And you would go from the lowest bucket to the highest.
You go from the lowest, the zeros bucket to the highest bucket. Yeah. Yeah. I will show you this in the animation in a second. Yeah.
If we're coding that, can we use ++ library classes?
No, use the queue we use for make up a queue. I mean, you've got one already from the other assignment, right? Like, just use a queue from the assignment. Just make it with integers instead of students or whatever. Pretty easy to do. And you've already got it built. Yeah?
What would happen to try to sort starting at the highest value? Would that just not work?
If you very good question. You mean if you started sorting here and there, you would end up with a slightly different order. I'll get to that in a minute. Okay, but first I want to actually show you the actual sort. Before we do that, I'll show you the sort in a second. Oh, I hope my Java thing works well. We'll see. The bins are queues, as we said. The time complexity, this is a little tricky. The time complexity is tricky because you're not doing comparisons now. Okay, you have to think about it a little bit different, right? In general, the complexity is the number of digits in your maximum number. In other words, if you've got 1,000 versus a 5, if you've got numbers that have 4 digits long, that's the one you have to do up to 4 times through the arrays, right? Because if you've got 5 digits, you have to do all up to the 10,000th place. Okay, if you've got 100 digits in your you'd have to do 100 passes, right? So that's going to be in there. And then for each one, you're going to have to go through, for each time, you're going to have to go through the list. Multiply those two together, you have n keys which have d digits. The complexity is on the order of d times n, which is actually linear. So we've actually got a linear sort here, which is better than a n log n sort, but it's hard to compare because there's lots more going on. For instance, how do you determine what the middle digit, the tens digit is? Well, you have to do some sort of modulus operator, or you have to do a division, and those things take time. So it's more than, so there is some extra time in there. So many times, Radix Sort will be a very, very, very fast sort. Sometimes you don't know your range of numbers. Sometimes you don't, there's other considerations where this isn't the best sort in the world. Okay? But it's in general a very good sort. Let's see if I can get this to work, the Java thing. I forgot to pull this up before. There it is, OK. And then missing plugin. Oh, no. Let's see. Let me try it in. I might have to postpone this till next time. All right. Let's see. Oh, small. OK. OK. Oh. Maybe. Ah, it's required. Darn. How about this? Let's see if they have it on the other computer. Hold on. What is the thing here? Hold on. Oops. There we go. It's too bad. I think it just installed Java, but oh well. HTTPS www.cs.auckland AC to NZ software slash ALGANIM slash Radix Sort .html. OK, let's see. Hang on. Where'd it go here? Desktop. All right. Come on. You can do it. Allow and remember. OK, hold on. All right. OK, that's a good sign that the little thing is going here. There it is. OK. Run it. Come on. I thought I did. I hate Java. They try, but it doesn't seem to work. OK, here's what I'll do. Oh, look at that. OK. All right. So it's hard to read up here. I would make it bigger up here. But here's our original numbers. 95, 18, 23, 47, 2902, et cetera. OK? And if we run, let's just run Radix Sort here. What it's going to do is it's going to empty all the bins. OK. And then it's going to process digit 1. So the cout's into 8 is the last digit. It's going to go into 8. OK? And I'm going to make this faster because this is ridiculously slow. OK. A little bit, no, still kind of slow. There we go. OK. So the 8s are going to go over in the 8 bucket. The 4s are going to go in 4. These are just queues. OK? And it's going to put all the guys in the right bucket like that. And the 0 is going to go over there. And then it's going to empty the buckets. And it empties the bucket from the 0 one first. OK? And that goes into, oh, where did it go? It's processing digit 2. Sorry. That's how it did it when it emptied the bucket. It said, oh, look, now these are all in the order. So now it's doing digit 2, OK, the tens digit. OK, and it's going to do that. And you're going to get the 1 there and then there. OK, so this isn't the best animation. I thought it would be better. There we go. So it's going to move up. Then it's going to do the 1 up here. And it's going to do the 3rd digit over 801. And now the 8's there and so forth. And you see how it's just kind of doing this one step at a time. OK. All right. And then let's see. It's going to have to do one more thing. I can't make this any faster, can I? No. Nope. No, next step I think is when you stop it. And it'll just do it one at a time, I think. OK, but anyway, I think we have one more to go here. And then, yeah, it'll do this last one. And they will now be in order, if it's taking its time. There you go. In the end, it will now be in order because it's doing the last one. OK. So you see how it's working, though, in terms of, like, maybe you can't. But go onto the website. You'll see. Make sure Java's loaded on your computer. And do that. OK. So then, well, we'll let it continue here. And then now it's going to be sorted. No, 801, 1608, or whatever. And then there you go. That one, and then that one, and then this one comes out. And then this one comes out. First in, first out into the buckets. OK? And then they end up in order. This is the slowest animation I've ever seen. Ah, all right. OK, so there, now we made an order. OK. Probably not worth it. OK. All right. So let me go back to here. And there we go. OK. So you've got the space complexity like that. Here's the question about if you do it in the most significant bit first, right? You end up with what's called a lexicographic sort. Take a look at this. BDE, bed, cat, bale, car, car. That becomes B, bale, bed, car, cat, D, and E, which is what you would expect, I would hope, right? But what if this was a single-digit number, and you were doing this kind of sort like this? Wouldn't that be like, well, OK, bad example. Wouldn't bed come before bale? Because if you were thinking about bed being a number, it's shorter and therefore less than bale. This would, if you did the least significant bit, you would end up with like bed and bale being reversed. OK? If you end up sorting numbers with the most significant digits first, what you do is it ends up looking like this. 1, 10, 2, 3, 4, like this, because notice the 1 is like before the other one. So it's kind of as if you had a little space after each number, and they were, instead of being a space before the digits. It's kind of like doing it backwards like that. So you end up with the wrong sort if you do it, like, well, depending on what you're trying to do. OK? So it's kind of interesting in that sense. All right, but that was a good question about that. All right? OK. Other order and sorting algorithms. Unfortunately, we don't have time to like go into too much detail with this, but you can have another order and sorting algorithm that will sort a list by only going through the list once. Okay? You've actually seen this before. I guarantee at some point in your life, you've seen a teacher sort things alphabetically, like a bunch of papers by last name. If you're a teacher and you're going to sort a bunch of papers by last name, what's the first thing you might do to those papers? Do you know?
Fan them all out.
Fan them all out, and then where would you? And then what's a good way to like start the whole sort? By A's, and then by B's and C's. So you have piles, right? You have like, when I used to do this with like lots of students and I had tests, I would put them in piles like A through C or something, and then do it like that. But if you had 26 piles and you put all the A's over here and the B's and the C's and the D's and the E's, you're basically sorting them into buckets, kind of like Radix Sort. But if you did it such that you knew the whole range, and you had enough buckets that one bucket would be per, let's say, name or whatever, you could actually do it by saying, OK, here's the first one. I'm going to put it in its bucket. And then here's the second one. I'm going to put it in its bucket. And if you have an array that's long enough to hold all the numbers in the whole range that you have, you take one pass through, and you end up with a sorted list, which is actually pretty cool. OK? At the end, what you do is you put them into these buckets that are zeros. And it's a little more subtle how you do it. You just put a count for the digit, the one you're on. And I'll show you an example, and then I'll let you guys go. The example is this. Let's say that you had an array where you knew that the maximum value was 15. Right? If you said, I'm never going to get a value bigger than 15. If you have another array like this for every number that you could have, you can then go through, and 6, that would make this one a 1, because that's 1, 6. And then 5 would make the 5, 1. And then 9 would make the 9, 1. 12 would make the 12, 1. Another 9 would make the 9, 2. And then the 4 and the 5 would make the 4, 1 and the 5, 2. And you end up like this. You've gone through the list once, and now you end up with a nice like this. And if you read through this list, and every time you get to a number, you just put that many of the number back in your original array, you actually can end up with it sorted. You go through and you go, OK, there's 1, 4, so I'm going to put a 4 here. There's 2 5s, I'm going to put a 5, 5. There's 1, 6, I'm going to put 1, 6, et cetera. You see how that works? That's another order n non-comparison sort. No other comparisons necessary. OK? And that's like what a teacher would do, maybe. You can also, if you have bigger buckets, you can then like do another sort on each individual bucket. That would be it. OK? All right. I've let you run 1 minute over. Sorry about that. I will see you guys next week.